All right, so for this problem, I'm going to go over the electrostatics question, the free response one that I assigned you guys. So for this question, we have three different charges, and they're oriented along the x and the y axis. And the distance from one of the charges, this one up here, is a distance a from the origin on the y-axis and has a value of negative 2q. This one is a distance of negative a along the y-axis. It also has a charge of negative 2q. And then this one over here has a charge of negative q, and it's a distance of 2a from the origin on the x-axis this time. And so this question is going to ask about electric force, electric field, and electric potential. And then it's also going to ask what happens if we take this charge and move it along the x-axis. So this one right here, it's already on the x-axis. What happens if we take it and we move it along? How does the force change? And so just to remind you, the force that we're looking for is called the electrostatic force. And it's equal to K, that electrostatic constant, times one charge times another charge, all over the radius squared. Sometimes you'll see this written with absolute values around the negative or around the Q values. And the reason for that is because you don't want the Q or the charge, you don't want the equation itself to tell you which way the force is pointing. You want to look at the equation and then look at the charges that you have and see which way the forces point. By that, I mean, if we have a negative Q charge here, and these other two charges are also negative values, we know that like charges repel, and these are all going to push each other apart. And so because they push each other apart, we know that if we're on the x-axis, the positive part, this one right here, we know it's going to push us to the right. And therefore, we define right as positive. However, if we position this negative Q charge over here, we know that the force is going to be negative. And so we know that the force is going to be pushing to the left. Same value of charges, but now the force points to the left. So we have to be careful about which way the force points. You have to think about the problem instead of the equation itself. All right, so in order to find the first thing that they want, which is the electrostatic force on negative Q, you have to find the electrostatic force due to each one and then add them up. But the good part about this problem is that right away I notice a symmetry. I notice that because these two charges right here are located on the y-axis and they're an equal distance from each other, I know that the y value of this force is going to cancel out. I know that the only contribution to the force, to the total force, is going to be the x component. So if I can find the x component, I can find the total force. And so what I did was I broke each one of these distances here into a little right triangle. And then I found the hypotenuse, because remember that hypotenuse represents the distance from the charge, and the distance from the charge is equal to our radius over here. And so that distance, if you do your right triangle and use Pythagorean theorem, you'll find that distance is square root of 5 times a. And so therefore the radius squared would just be this value squared. And then we just have to know what each of those forces are in the x direction. And so if I were to look at this triangle right here, I could say, okay, if I define this as my angle theta, then I can say that sine theta is equal to 2a over the square root of 5a, which simplifies down to 2 over root 5. So the y component is just going to be our normal force, our regular total force component, our hypotenuse of our force, times this y component right here. And then to get the total y component, we just add both of them, or I'm sorry, the total x component, we just add both those together. And so what we're left with is we have the electrostatic force is equal to K times 2Q times Q times 2 all over the square root of 5. And then this is all over 5a squared. And then what I'm going to do is, because we have two different charges and there's that symmetry there, I'm just going to multiply this by 2 to take into account the other charge, because this would be the value of one of them. So if I multiply this by 2, what am I left with? Well, I'm left with 8q times 5 times square root of 5 times a squared. So it's a little hard to read, but this is 8q all over 5 times square root of 5 times a squared. Now you could leave this as q squared, that's totally fine, but I just left it like this just so we can see the two different charges in that equation. So that's your electrostatic force on negative q due to the other two charges. The next part of the problem wants to know about the electric field and the electric potential at the origin. So it wants to know if you were right here, right at 0, it wants to know what electric field do you feel and what electric potential you feel. Well, if I look at this, again, they make use of symmetry in really useful ways here. Because if I look at this, I can say, okay, this contribution on the y-axis is going to be canceled by this contribution on the y-axis. And so really, all we have to worry about is the x component of that electric field. And the only x component is just this negative q charge over here. So therefore, our total electric field then is given by kq over r squared. In this case, q is negative q. I'll leave it as positive for the same reason I leave the force as positive. But it's going to be q, k times q, all over the radius squared, which is 5a squared. All right, so, oh, I actually made a mistake here. So the radius is actually not 5a squared, or the radius squared is not 5a squared. If you notice, the radius is just the distance between the origin and this charge. They give that to you as 2a. So therefore, that squared is going to be 4a squared. So this is still radius squared, but now the actual radius is just 4a squared. So our final answer is kq over 4a squared. That's the electric field. Remember, electric field has a direction to it. And in this case, it's going to point this direction in the direction of, it'll point in the direction of the negative q charge. And so our last thing is to calculate the electric potential at the center. That is not direction dependent. It's not a vector. And so these two don't cancel out. And so all you have to do is you have to add up each contribution from each of the charges. And so what do we have? Well, for these negative 2q charges, well, let me first write the equations. That's kq over r. And so if I add all of these up, I'll put a little epsilon in there, or sigma. I'll put a sigma there to represent, we just add up all those individual charges, or all those individual potentials. And so the first one, we have k times q, which is 2q, all over the radius, which is a. And then we have plus k 2q over a. And then we have plus kq over 2a to represent this third charge over here on the x-axis. Now, all you have to do is get like denominators and add all these up, and that will be your answer, whatever you get when you add those three up. And that's our electric potential at the center. All right, and the last thing it wants to know, what does the graph look like for this q charge if you were to take it from really far out here, so pretend this charge is actually way out here, and then you bring it closer to the origin, and then it passes the origin. And so for that, so we want to know how the force changes with respect to the distance. And so for that, well, let's think about it. Let's think, first off, I always like to get what my zero value is. I like to get what happens at that origin, just because that's easy to see. And I say, okay, well, if the distance is 0, right? So if it is directly on the origin right there, it's going to be halfway in between two charges of equal value. And so those are all going to cancel out. If you think about it, if you're at the origin right here, those two charges above you are just going to cancel out. And so what we're left with is 0 right here. And so our origin is going to be 0. All right. Well, what happens then if we're at really far values of q? Well, if we're at really far values of q, I'm sorry, not of q, of x. If we're really far away from here, we should see that our force starts to decrease and asymptotically approach 0. It's never quite 0 because the radius, as the radius increases, the force does decrease, but you never actually get a 0 out of it. but it does get really, really small as you go away from it. But as you get closer to it, it starts to pick up like this. And then it kind of goes down, and it kind of goes like this. So what we see from this graph is we see that if we're really far away from it on either side of these two charges, if we're really far away from it, the force is essentially zero. This force is essentially zero. But as we get closer to it, it increases. So for instance, if we're on the negative side of this, it increases in the negative direction. Why is it negative? How do I know it's negative? In the first part of the video, I said that don't worry about the signs in the force equation. So how do you know it's negative? Well, in the question itself, it tells you that if the force is pointing to the left, then we define that as negative, and that's pretty conventional. So therefore, because if we're on this, if we're to the left of the x-axis, we know that like charges repel. So if we're on the left of the x-axis, or on the left of the origin of the x-axis, we can see that that force will also be pointing to the left. And so therefore, we have a negative force right here when we're at negative values of x. Just like that, if we're on the right side of it, we're going to be pushed to the right. Again, like charges repelling, pushing to the right. Right is defined as positive, and so therefore we'll have a positive force when we're to the right of the origin. That force will increase, and then at a certain point it will start to decrease as we get farther and farther away. And then when we get really far away, it essentially goes to zero. All right, so let me know if you have any questions.